Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're tackling one of the most exciting frontiers in robotics. How can robots move beyond simply following commands to truly collaborate with humans, understanding our intentions and anticipating our needs? Just like another human teammate? Our guide for this deep dive is Chapter 13, titled A Dynamic Neural Field Approach to Natural and Efficient Human-Robot Collaboration, authored by Wolfram Erlhagen and Estela Bicho from the insightful book Neural Fields Theory and Applications, published in 2014. This chapter presents a compelling framework for building robots that can interact with us in a more intuitive and human-like way. So, how do we design robots that can understand our unspoken cues, predict our next move, and seamlessly integrate into our daily tasks? The authors argue that traditional, top-down artificial intelligence, or AI, approaches, which rely on symbolic logic and discrete processing stages, often fall short in dynamic, real-time human-robot interactions. They're too rigid, too slow to adapt to the fluid nature of human collaboration. Instead, this chapter champions a more bottom-up approach deeply inspired by how the human brain itself operates, dynamic neural fields, or DNFs, and the overarching dynamic field theory, or DFT. Let's quickly recap these core concepts. As we've discussed in previous episodes, neural fields are mathematical models that describe the collective activity patterns of large populations of neurons as continuous waves or landscapes of brain activity, rather than individual neuron spikes. Dynamic field theory, or DFT, then explains how these fields evolve over time, forming stable patterns like bumps of activity that represent specific cognitive states or decisions. This framework provides a systematic way to endow a robot with crucial cognitive functions. One of the most critical inspirations for this robotic framework comes from the field of neuroscience, the mirror neuron system. Discovered first in monkeys and later in humans, mirror neurons are a special class of brain cells that fire not only when an individual performs an action but also when they observe someone else performing a similar action. This phenomenon gives rise to what's called the action resonance mechanism. It's believed to be fundamental to our ability to understand others' actions, infer their goals, and even empathize with them without needing explicit verbal communication. Imagine how we instinctively understand someone reaching for a cup. The mirror system helps us grasp their intention. This mechanism is absolutely vital for a robot to truly understand human intentions. The authors propose a sophisticated, multi-layered DNF model for joint action, which is organized as a large-scale network of these reciprocally connected neural populations. Think of it as a series of interconnected brain regions within the robot's control system, each responsible for different aspects of collaboration. The action observation layer, or AOL, processes what the robot sees the human doing, for instance, the type of grasp they use on an object. This information feeds into the action simulation layer, or ASL, where the robot internally simulates the observed action, activating its own motor representations. This is where the mirror mechanism comes into play, helping the robot infer the human's goal. The inferred goal then activates a representation in the intention layer, or IL. Meanwhile, the object's memory layer, or OML, maintains a memory of all objects in the environment and their locations. And the common subgoals layer, or CSGL, keeps track of the shared task knowledge, what has been done, and what needs to be done next, both by the human and the robot. Finally, all this information converges on the action execution layer, or AEL, where the robot selects its own complementary behavior. The dynamics within each of these DNF layers are governed by mathematical equations similar to the Amari neural field equation, which describe how activity patterns form, stabilize, and interact. These dynamics allow for self-sustained bumps of activation, which are crucial for the robot's working memory, enabling it to hold information temporarily even when sensory input is missing. To put this theoretical framework to the test, the researchers conducted human-robot experiments involving a collaborative toy assembly task. The robot, named Aros, and a human partner worked together to build a toy vehicle from its components. The results were truly impressive, showcasing the DNF model's ability to enable goal inference. The robot could infer the human's intention, e.g., whether they were going to attach a wheel or hand it over, simply by observing their grip type, even if the hand-object interaction was partially occluded. Taking initiative, if the human hesitated or didn't show an immediate action, the robot could take the initiative, proposing the next logical step in the assembly process based on its shared task knowledge. Anticipation, the robot could anticipate the human's future needs, preparing and offering the next component required for the task. understanding partially occluded actions even when the human's hand was hidden behind an obstacle. The robot's working memory of the objects in the scene, combined with its DNF-driven goal inference, allowed it to accurately predict the human's action. This research demonstrates that dynamic neural fields provide a powerful and biologically plausible framework for designing autonomous robots that can engage in natural and efficient human-robot collaboration. By leveraging neurocognitive principles like the mirror system and the dynamic properties of neural fields, these robots can move beyond simple stimulus response behaviors to genuinely understand human intentions, anticipate needs, and adapt in real time, making them true teammates. This work represents a significant step towards a future where robots can seamlessly integrate into our lives, understanding and assisting us in ways previously thought impossible. It's a testament to the power of looking to the brain for inspiration in building intelligent systems. That's all for this episode of DeepVisus. Join us next time as we continue to explore the intricate ways vision meets depth in the fascinating world of neuroscience and robotics. Stay tuned.